All right, in this second part, we're going to be looking at some examples of collisions. So how can we calculate momentum with a collision? So the first thing you want to do with any collision is you want to figure out what is the momentum of our objects before the collision occurs. So remember the momentum, I made that really small. Momentum is equal to mass times velocity. Momentum again is that P, which is really rho, a Greek letter. So before the collision, we need to calculate the individual momentums of each object. So let's say we have two carts that are going to collide into each other. So I have a cart A, and before that collision, the cart A has a mass of 50 kilograms, and it is traveling with a velocity of 100 meters per second. And it's going to crash into cart B. And cart B has a mass of 4,000 kilograms and a velocity of 0. So it is standing still. It is not moving. So we want to calculate what our momentum is before of each of these objects. So momentum is mass times velocity. So for cart A, we're taking 50 times 100, so that's going to equal 5,000. And then here for cart B, we have 4,000 times 0, so we have 0 momentum with our second car. So when we add these up and look at our total momentum before, because remember with the law of conservation of momentum, our momentum before and after has to equal each other. All we're going to do is add these two momentums. Well, we have 5,000 plus 0, so that's just 5,000. Now, this is the easy part because momentum before, you're just looking at your objects that are not even crashed into each other. After the collision, there's two different ways. So remember, we have elastic or inelastic. Depending upon whether it's elastic or inelastic, we're going to treat each situation a little bit differently. So that's why you have to be really careful about looking to see what type of collision it is. So after our collision, if we have an inelastic collision, so remember inelastic collision, that's where they're going to stick together. So let's look at, so if we were to draw a diagram of it, say I have cart A, and it is traveling, and it's going to run into cart B, that's not moving, and then afterwards they're going to be stuck together, and they'll be moving together. All right, so when we look at our momentum afterwards, okay, so our momentum afterwards is still going to be mass times the velocity, but we have to remember our mass here, we need to find the total. So it's going to be the mass of A plus our mass of B. So that's our 50 times 4,000, so that's 40, 50. And then we can plug it in here, and then we know our momentum beforehand is 5,000. We can figure out what our velocity is going to be afterwards. So momentum before equals momentum after. So our momentum before is our total momentum, so that's our 5,000. And we have our mass, so 40, 50, and we're looking for a velocity after they hit each other. So all you have to do is divide, and you end up with a velocity of 1.23 meters per second, which makes sense. So we were going 100 meters per second beforehand, but our object was only 50 kilograms. It's running into a 4,000 kilogram object. It's much more massive, so that's really going to slow it down. So this is for an inelastic collision. Our momentum after, we're going to look at our total mass because they're stuck together, so our mass changes, and then we can use that to find our velocity. All right, so let's look at our other type of collision. So this is when they bounce off each other. So if we look at our diagram, it's still the same before. So we still have A moving, B is not. And then afterwards, we would have A would not be moving because A would transfer all of its momentum, and then B would be moving. This one's a little bit trickier because we have to remember that our momentum afterwards is equal to the two momentums that we have here. So we would have to add these two momentums together. So when I'm looking at my calculations, so momentum before is still that 5,000. Okay. And then our momentum after is going to be the momentum of A plus the momentum of B after. So mass of A times the velocity of A plus the mass of B times the velocity of B. Now, in this situation, A is not moving. A has stopped. So we know that this is 0. So we can say the momentum after is going to just equal the momentum of B, because B is the only object that's moving. So we have 5,000 equals our mass of B times the velocity of B, which is what we're looking for. So our mass of B is 4,000. And our velocity ends up being 1.25. Again, notice not much of a difference between these two for our velocities because B is so much bigger than A, it doesn't make much of a difference. All right, so that is the end of part 2.